We have been looking at the synthetic aspects of materials in the past few lectures, and there is a significant divide between chemical approaches and non-chemical approaches. I have highlighted to you in one of the earlier lectures about sonochemical synthesis, where we use ultrasound waves to synthesize materials. In this lecture I would like to focus on microwave processing of materials, and mainly this is coming under the category of unconventional wet chemical approach. As you would see in the following slides, how electromagnetic radiation can be effectively used for synthesizing materials. So, in the next few slides let me highlight to you the importance of electromagnetic radiation interaction with matter and how this can be usefully exploited for making materials. Just to familiarize yourself where we stand as far as this approach is concerned in the electromagnetic spectrum, this is the microwave region, and the size of wavelength is of this order, where it is from centimeter to millimeter, a size of an ant we can say, and the frequency is of the order of 10 power 10 to 10 power 12. Therefore, it is usually categorized under gigahertz or megahertz, and one of the longer wavelength region next to radio wave, and therefore this is sandwiched between radio wave and infrared. And as you know, several of this electromagnetic radiations can be used either in the study of synthesis or in the study of spectroscopy of the materials. As we saw from the earlier slide, microwave is placed between radio wave and infrared. Usually the region that is of more interest for material synthesis is this 2.4 gigahertz region. And just another mention about this electromagnetic wave is you have two vectors, one is a electrical vector and a magnetic vector, which are perpendicular to each other, and that constitutes your electromagnetic wave. Therefore, if a material possesses some dipole, then the electric field component has to interact with the matter, or if the material has a moment, magnetic moment, then the magnetic vector of the electromagnetic radiation should interact with such a matter. So, either way, when electromagnetic radiation is interacting with molecules or materials, there will be some response of different order. So, that way we will be actually using the electrical vector of the microwave radiation to interact with matter, and we would see in the next few slides what governs this interaction. As far as the theory of microwave heating, microwaves are not ionizing radiation, they are soft. Okay. Therefore, this is not a ionizing radiation, but largely this can be used to excite or lift the potential energy of the molecules. So, when the potential energy of a molecule is lifted up, then the kinetic energy barrier or the energy barrier that is restricting between the product and the reactant will be lowered considerably. So, we are trying to use the potential energy of this molecules to overcome the energy barrier in order to give resultant products. As you would see, microwave energy is largely below the energy necessary to break bonds. Therefore, it is not going to make or break any bonds, but it is going to interact, but the heating effect does not come from breaking of bonds. So, if you compare the quantum energy that is available from microwave radiation, let us say 2.5 gigahertz, then you are talking about a very low electron volt energy, and this energy is not sufficient to break any bonds. For example, think of hydrogen oxygen bond 5.2 eV, or hydrogen bonding in water is of 0.21. So, even it cannot overcome the hydrogen bond. Therefore, the secondary effects of microwave interaction with matter is what is going to bring about synthesis. Therefore, this is not a bond making or a cleaving process. So, when we think of the wavelength of such microwaves, you can think of the dimensions to be 1 millimeter to 1 meter. That is why in conventional microwave ovens that we have in our kitchen, you actually have a perforation, metal foil in front of you, which is having very fine holes less than 1 millimeter, so as to give you some transparency for you to see what is going on inside. At the same time, it will avoid the leak of the microwave from coming out of the commercial oven. Frequency allowed for commercial, medical and scientific application is of this order. Therefore, it will not easily come through these small openings that is available in the conventional or commercial ovens. There are many ways that we can interpret the heating, but there are two specific causes by which microwave heating can be achieved. As you know, the molecule, when you keep a molecule in a electrical field, let us say H nu, then the molecule actually undergoes deformation. In other words, there is polarization. Suppose it is in the axis, molecular axis, then this particular molecule will deform like this, and thereby it will induce a polarization. So, the molecule will actually deform in the axis, molecular axis, when light is applied. Therefore, there is a polarization in this form, and suppose we apply the light in this direction, electromagnetic radiation, then the deformation will happen in this form. In any way, we actually have a polarization that is induced, and this is anisotropic in nature. So, this dipole will actually rotate, or this dipole will oscillate with the microwave frequency. As a result, there will be interaction between the material, molecule, or any solid for that matter with the matter, and once dipole is introduced, it will bring about a net polarization, and this net polarization is the governing factor for the interaction of microwave energy with the material, and therefore, there will be two mechanisms which will actually govern. We will see in the next few slides. So, the frequency dependence of the several contributions to polarizability can be mapped up this way. The power loss, microwave power, is therefore proportional to the electric field, and alpha comes as a proportionality constant, where alpha is nothing but polarization or polarizability, and this net polarization is actually governed by three factors. One is dipolar polarizability, and ionic polarizability, and electronic polarizability. But if you actually look at the frequency mapping and what are all the polarizability factors that become active in the microwave region. So, if you look at the microwave region here, the dipolar and ionic contributions are maximum, and therefore, the interactions of the microwave radiation with matter is principally governed by these two mechanisms. So, dipole rotation is to do with the dipole that is oscillating in a molecule when it is kept in an electric field, or it could be the ions that are coupling with the electromagnetic radiation, and therefore, they will oscillate according to the frequency. Alignment with the oscillating electric field, and therefore, there is loss of energy in the form of heat, which forms the mechanism. The animation of this is given in this cartoon. As you can see here, when microwaves come, the dipoles actually oscillate in this fashion. They do not rotate, but they oscillate with the phase. So, when you bring any molecule in phase with the frequency of your microwave, then they start oscillating with the keeping phase with the electromagnetic radiation. So, this is to do with dipolar polarization, and in the case of conduction mechanism, it is the ions that oscillate with the electromagnetic radiation. In either case, as you would see here, this oscillation actually brings about frictional force. So, when there is frictional force with the neighboring molecules, there comes heating. So, this is not a breaking of bond, but the heating actually comes from frictional force that is coming from the dangling of these bonds. As a result, a local heating is generated. So, this local heating actually maximizes a uniform heating in the whole material rather than the heating coming from one particular direction. Therefore, this particular heating effect that is generated due to microwave is much more special than any other form of heating. So, this is another way that we can construe how this water is getting heated. In a conventional microwave, if you just put water, within 30 seconds or so you get it boiling hot, and this is how it is. There is a permanent dipole here because of this polarization of charges, and this is the axis perpendicular to the molecular axis, and molecules actually will be rotating in this fashion. So, molecules will rotate and then again it will go back. So, it is more of oscillation, not a continuous rotation, it is more of a oscillation of this form, and this oscillation will actually hit other neighboring water molecules. So, when there is a global effect where all the water molecules are oscillating with each other, then the frictional force actually brings about the heating, and same is true for the ions. So, the ions do also oscillate in phase with the microwave radiation, producing heating. So, when we think about this heating, do we have any numbers that we can look at, and what is the factor that governs the heating of these materials? There are three parameters that we should bear in mind, and we need to moderate this in order to get maximum heating effect. One is dielectric constant E prime, and this is to do with the material itself that is interacting with microwave, and this dielectric constant is dependent on the polarizing level of a molecule in a electromagnetic field. Sometimes if you have a molecule with a permanent dipole, then already it is polar, therefore it will couple. But if you have some molecules, maybe non-polar molecules or aprotic molecules, then those will actually have a induced dipole moment in the microwave, therefore that will also interact. So, the essential factor is the epsilon or E prime, which is unique of the material itself, and the second factor is dielectric loss E double prime, and this is the efficiency of the microwave conversion into heat, and this E double prime is nothing but conductivity over frequency, and therefore we can call or we can have a measure by which the interaction of the microwave radiation with the material can be gauged, and this is given by tan delta, and this tan delta is nothing but E double prime over epsilon prime. So, this is called as tangential loss or loss tangent, and loss tangent is nothing but the material capability to absorb microwave. So, if loss tangent is approximately close to unity, then you say there is maximum capability of the material to absorb. Suppose it is less than 0.1, then it is a material which will couple very poorly. So, if you have a data for tangential loss, then you can easily map what sort of material can be used for the reaction, and you can fine tune on the frequency to affect this. In case of polar compounds, actually your conductivity is more compared to omega, therefore your tan delta will be very close to 1. So, the dielectric parameters are governed by this equation, as we saw. Tan delta is equal to E double prime by E prime. We call this as dielectric loss, and we call this as dielectric constant of the material, and this is the loss tangent. And if you can map several of these compounds which couple with microwave, we have three categories. One is strongly coupled molecules, and the one which tops the order is ethylene glycol, where the tan delta is of the order of 1.350. Okay. So, and as you would see, these are all polar compounds. Most of these polar compounds are very close to unity, therefore, these are best microwave absorbers. But if you go further down, you can see a region where there are some molecules or organic solvents which are mediumly coupled, so therefore, they may not really bring about the necessary heating effect as you would see, and there are other ones which are very reluctant to couple with microwave. Therefore, the tan delta value gives us a measure of what sort of combinations that you can choose for microwave synthesis. Here are some more materials which gives you the tangential loss factor. As you would see here, water is a better candidate compared to some of the polymers here, and Teflon. For that matter, Teflon is very reluctant, therefore, Teflon can be used as an inert material even to conduct many of the reactions. For that matter, in conventional microwave synthesis, Teflon tubes are used, or Teflon boards are used, or Teflon bombs are used. So, mainly because they do not interact with microwave. So, this can be used as a substrate or a holder for conducting reactions. So, the tangential loss factor is one measure by which we can gauge what sort of material can interact with microwave. Now, when we look at this dielectric heating, we need to understand that the dielectric heating really brings about a drastic change compared to the conventional heating. For those who are familiar with organic synthesis, usually all the reactions are conducted in oil bath or in sulfuric acid bath, because you can go up to 350 degree centigrade maximum to conduct your reactions. But if you look at the zone that you try to generate, usually there is a gradient here, and temperature gradient is maximum in this region, and you do not see the voluminous heating that is happening in a conventional oil bath. Or even if you have a electro heating furnace, the heating will come from all sides, and therefore, there will be a clear temperature gradient and voluminous heating cannot be achieved. Whereas, in the case of microwave, because it depends on the dielectric parameters of the material, there is voluminous heating in the material, and therefore, there is no temperature gradient that you would see, and as a result, if you are looking for any phase separation or any other possible impurity formation, this can be very easily avoided in microwave heating compared to electro heating. So, this is a very crucial dividing principle between microwave heating process and the conventional process, which really makes this a very good candidate to try a variety of reactions. So, when we think of using this microwave heating for synthesis, we need to understand what can be the holder, what can be the vessel in which we can use. Therefore, we should use a vessel which is actually transparent to microwave, which means it does not interact with microwave. So, it will allow the material to microwave to pass through, but react only with the sample. Therefore, if you have a low loss insulator, for example, and this low loss insulators are transparent to microwave, as a result the penetration is total. Okay. So, glass, for example, or any ceramics, they are transparent to microwave. So, heating can be very well achieved. So, crucibles of glass or something made of silica or alumina, these can act as a very good agent. Even Teflon can act as a very good agent for microwave to go through. Metals actually coupled with microwave, therefore, they are opaque. It would not allow the microwave to pass through, so it gets reflected and that is why you have a shield in your commercial microwave which is a metal shield, therefore, it will actually reflect the microwave to the center of the cavity. As a result, the material that you want to heat can be effectively heated. Therefore, metal is opaque a candidate, and as far as the absorbers are concerned, lossy insulators can allow partially the microwave to go. As you would see, it propagates, but then it gets dampened, and therefore, the penetration is partial to total. Or if you have in such lossy insulators some metal ingredients like this, as you would see here, then this can actually allow microwave to get absorbed, and therefore, you can achieve a partial or total penetration. So, this gives us some idea about the range of material that I can choose, those which are opaque to microwave and those which are transparent to microwave. And as a result, we can say reflective ones are metals, water is a very absorptive metal, and those which are transparent to microwaves are polymers. Polymeric stuffs are microwave transparent, therefore, you can use that as containers. Now, every kind of reaction performed under classical heating methods can be performed under microwave radiation. Therefore, this sort of chemical synthesis is actually categorized as microwave assisted reactions, and in microwave assisted reaction you can aim for both solution approach as well as solid solution approach. So, if you want solid state reactions, that is also possible. Suppose you are bringing two solids and this has to be formed, usually such reactions are aimed at under sealed vacuum conditions. So, vacuum sealed capsules can be used for bringing about solid state reactions to bring the solid interaction into closer proximity, because usually when solids couple with microwave, there will be a plasma generated, and this plasma can bring about a voluminous heating, and therefore, this is done in sealed tube experiments mostly. For volumetric heating. So, we can actually go for any sort of reactions there. Neat reagents are possible, as well as solid supports are possible. So, variety of solid state reactions can be achieved. Similarly, solutions we can try with apolar solvents or aprotic solvents and polar solvents. In case of apolar solvents, we need to induce some sort of microwave susceptors which will actually bring about the microwave coupling. Therefore, either of this range can be achieved. So, what are the advantages of microwave heating? Why we have to use microwave heating? Number one, it is reduced reaction time, or if you think about sintering, I will come to this issue later in some of the examples. We can tremendously lower the reaction time scale, and we can also avoid side reactions. Therefore, microwave heating is more selective, and especially in organic synthesis. In today's lecture, I will not be able to give you more examples on organic synthesis. I will concentrate more on inorganic materials, and another thing is it is more specific in nature, and therefore increases the yield of the reaction, and it gives improved reproducibility and also increased density of film when we try for some film fabrication approaches. So, when you look at microwave effects, one of the main ingredients there is the thermal effect in this microwave heating, which achieves a high reaction temperature at high heating rate, and therefore, it affects the energy of activation. So, the reaction rate can be fastened by orders of magnitude. So, because of this, we try to use the thermal effects as a source to speed up the reaction, and the way that we can do that is of two forms. Either we can go for a single mode cavity instrument or multi mode instrument. what we have in our kitchen microwave is actually a multi-mode instrument, where you have a magnetron which will generate your microwave, and this is guided by a waveguide, and this will finally lead to a open cavity where it will be confined, it will get scattered everywhere, but then reflected so as to concentrate only on the sample. So, this is a multi-mode cavitation, and single mode instruments are also available, where you generate microwave and this is actually channelized through a waveguide only to hit at a particular sample. For organic reactions, this sort of single mode cavity instruments are also possible. I will show one or two commercial instruments which can do the job, and as you would see, microwave is also the source material for electron spin resonance, where a magnetron will generate microwave, and that is actually guided through a waveguide to the sample. So, single mode instruments are already in use, but multi-mode instruments actually helps us with larger amount of samples. There are different versions of microwaves that are available. I do not mean to promote only multi-synth equipments, but there are several other commercial instruments that are available. I will show some which are used in our own laboratory for reference, but this is a very good sum up to show what sort of features can be achieved. We can go for mono or multi-mode using this sort of a cavity, and if you look at the inside view picture, you can actually do a scale up of that with the many containers here. So, you can go for a easy scale up in a parallel fashion, and you can also engineer open vessel reactions. For example, these are for open vessel synthesis. These are Teflon bombs that can be used for high pressure vessel studies. As you can see, this can be kept inside a bomb and then can be mounted here. So, this looks more like a lab station, where you can have a parallel synthesis of several units of your sample tubes placed simultaneously, and therefore you can scale it very easily. So, from a simple multi-mode cavity, you can achieve many things. One, you can look this more like a muffle furnace, but then you can do open system reactions. If you want to, you can even purge the system with gas. So, this is possible, or you can do closed system. As you can see, this is confined to a bomb, and we can try to measure the pressure release there. So, parallel screening can be made, and Teflon bombs can be housed like this. So, either you can do open system or closed system reactions, and the buzzword here in microwave heating is the shorter reaction scales, reaction time, and as a result the solution actually gets a uniform heating. So, we can go for any sort of reactions that we are looking for. But when we come to solids, we need to understand that it is not as simple as the solution process. As you would see here, this is a good example of a glass ceramic, and this is a hot pressed boron nitride, this is alumina, this is silica, and this is again 99% alumina. In all this, if you look at the tangential loss factor, these are very low, and you need to expose these materials for a longer time scale in order to really achieve a considerable amount of microwave absorption, and this region in such insulators is actually referred to as thermal runway. This is called thermal runaway, meaning there will not be effective coupling of microwave with this material until you generate a minimum energy or temperature. Only after the sample reaches say 600 or 700 degrees centigrade, then you will be able to scale up or maximize on the coupling, and therefore when you look at the insulating oxides, one of the or ceramics in general, one of the important thing that we need to understand is it is not as quick and fast as solution route. Therefore, this thermal runaway is a very important parameter when we are looking at solids when they interact with matter. So, I will take you through some of the examples from now on. Some of the examples are from our own group, and let me first start with those examples. The one thing that is very popularly used nowadays is microwave coupled polyol reaction, and this is a commercial instrument that we have from CEM Corporation USA, and this is a Voyager unit which actually has a magnetron which is designed in such a way that you can get the microwave focus to the center of the cavity here. So, this you will get a voluminous heating, only thing the size restriction is there, but you can actually use it for both open vessel as well as closed vessel reaction, and this is the way you can generate the microwave concentrating on the middle of the sample region. So, let me take a issue of zinc oxide formation, and we can do alloying of the zinc oxide either with cadmium doping or with magnesium doping. And as you would see here, the reaction is very simple. You can start with the nitrate, either zinc nitrate or magnesium nitrate and cadmium nitrate as you would desire, and you can use urea to hydrolyze, and ethylene glycol is both used for hydrolyzing plus as a solvent. As you have seen in one of the previous slides, ethylene glycol is actually having a strong tangential loss, and therefore, this is a very good solvent that can be used for reactions. So, in this example I will show you how size dependent photoluminescent properties can be generated in dumbbell shaped zinc oxide multipots prepared by microwave assisted polyol route. As you would see here, polyol synthesis involves high boiling alcohols with more hydroxyl groups. More the hydroxyl groups, then the tangential loss gets maximized. Therefore, the alcohol can do two jobs, one is to reduce and the other one is to act as a solvent, and the mechanism is proposed via two types. One is crystallization of the metal hydroxides and dissolution of the metal hydroxides and further reduction by alcohol to give corresponding metal nanoparticles. Okay. So, let us take the case of a simple reaction of zinc oxide before we consider cadmium and magnesium doping. So, I can actually vary the exposure of this mixture to 1 hour to 6 hours and then look at the property to understand what really is important. Now, in this case you can see 1 hour exposure, 2 hour exposure and 6 hour exposure gives very highly crystalline zinc oxide powders. So, there is no doubt from the X-ray mapping that you can see this typical hexagonal pattern that is coming out. Therefore, you would not like to doubt on the X-ray purity or the composition of this oxide, but what you should understand that the exposure does control the particle size, and as a result the other properties can also get altered, and that is what you would see from the other cartoon here. At 1 hour you can see that they are almost forming sort of pots, multipots of zinc oxide, and you do not seem to see any secondary effects or any phase separation here. Therefore, these are quite impressive. 1 hour and at 2 hours seemingly these multipots have grown in size, but when you go to 4 hours and 6 hours the sort of length scale of these multipots are vanishing and they are going more into smaller crystallites when you go for 6 hour time scale. So, does this growth factor or the shape and size of the zinc oxide nanorods, do they have any influence on the property? If you look at the absorbance for a 2 hour exposed mixture and a 4 hour exposed mixture, you would see the optical band gap is nearly the same. So, you would not think that there is anything extraordinary happening, but if you look at the photoluminescence spectra of the 2R sintered 2R exposed and 4R exposed mixture, you can clearly see the photoluminescence is totally different. In 2R exposed case, you get a very characteristic sharp 380 nanometer band, which is nothing but your band to band emission, and this is exactly what is needed as far as zinc oxides are concerned. But when you expose it further, the subsequent nucleation actually brings about defect chemistry into zinc oxide. As a result, you do not see this 380 nanometer peak, but you see a dominant surface induced defect induced emission. As a result, you do not see this characteristic 380 nanometer peak anymore. Therefore, the way you expose the mixture or the starting material to microwave, it may not show macroscopically any defects, but it subsequently will induce some amount of defect chemistry into it. Therefore, this study would help us to understand how much of microwave exposure is needed to control the physical properties. As you would see, the growth of these multipods are also kinematic in nature. Initially this zinc oxide nuclei are formed, and they form subsequently single nanorods, and these nanorods get fused like a dumbbell shaped ones, and these dumbbell shaped rods further they get fused like this fashion into multi rods, and all this is kinetically controlled. And therefore, if you want to stop the defect chemistry, then you need to stop at a particular size. If you go for a very long exposure, probably you will get very interesting facets of zinc oxide rods, but essentially they lack in clarity as far as the photoluminescent property is concerned. Similarly, for cadmium, let us say if we can achieve easily doping for 20% and 50% cadmium oxide, and X-ray will not give you any clue, but once you see here carefully the SEM feature, these are all zinc oxide rods. You can see the hexagonal feature on the top of this rod, but for 50% you do not see the same morphology. And if you carefully look at the decomposition temperature and the heat of formation of these oxides, we can get a clue. For zinc oxide, the decomposition temperature of zinc hydroxide is only 125 degree, and therefore it is very easy for us to get zinc oxide nanorods. Whereas when we dope cadmium into it, cadmium hydroxide is initially formed, and for cadmium hydroxide to get subsequently reduced to cadmium oxide, it is very reluctant because the temperature that is needed is 232. As a result, what you see in the previous view graph, this is nothing but cadmium hydroxide, and this is totally segregated out. As a result, you do, and this is amorphous in nature, so it will not show off in your X-ray as an impurity peak. Therefore, we need to take care as to how the decomposition temperatures can affect the final oxide formation. I will show in the next few slides another example of magnesium hydroxide doping in zinc oxide. In the next example, we can again look at another issue of magnesium doped into zinc oxide. Zinc oxide is hexagonal in nature, therefore, when you look at magnesium doping, any segregation of magnesium oxide will come out as a cubic phase, then you can easily map. But what we see in reality is when you use polyol synthesis, you again see a very highly crystalline zinc oxide with no presence of magnesium hydroxide. And if you look at the TM, it does not show any phase segregation. So, one can actually confuse this to be a solid solution of magnesium oxide in zinc oxide. But what you see in effect is magnesium hydroxide is getting formed, and because as I showed in the earlier slide, magnesium hydroxide decomposition is only at 350, whereas zinc hydroxide is forming at 125 degree C. Now when you try to dope any amount of magnesium hydroxide, this actually gets surface coated on the zinc oxide nanorods, and therefore, because magnesium hydroxide is amorphous in nature, you would only see the zinc oxide nanorod pattern, and you would not see any presence of a phase separation. Whereas, if you try to heat this zinc oxide rods which are coated with magnesium hydroxide, then at 1000 degrees C this gets converted into magnesium oxide, and then this magnesium oxide gets partially doped into zinc oxide, which you can see from your PL. Slowly the bandage is actually going from 380 down to 240 or so with a blue shift in the absorbance. So, we need to have an idea about the individual decomposition of this hydroxides, so as to map for effective doping of these solid solutions. There are many examples from other groups which I would like to quote. One is inorganic synthesis of nanoparticles. Let us take the example of platinum and ruthenium nanoparticles. These are used for a variety of purpose, and again here ethylene glycol can be used. In a conventional heating, actually this would require a reflex at 160 degree for 3 hours, whereas in microwave the whole reaction can be completed in just 15 minutes exposure. Therefore, you can speed up this reaction. Not only that, this platinum ruthenium catalysts show a very different behavior. Look at the X-ray analysis. So, X-ray analysis of platinum ruthenium which is exposed to microwave clearly shows a very different X-ray compared to the conventional heating procedure, where here you see PTRuO4 type of a X-ray pattern which is highly crystalline, whereas in this case you see a broad or X-ray broadening in this peaks, which is indicative of nano size. So, whenever there is X-ray broadening, you talk about a nano size regime, and that is the reason why it is not highly crystalline. So, if you look carefully at the TEM pictures, both the pictures here enlarged versions, there is more agglomeration in the case of conventional heating method, where you see very dark patches, whereas the particles are much thinner and finer and nearly separated in the case of microwave sintered samples. Therefore, making nanomaterials, microwave can still perform a better job compared to conventional heating. And if you want to make cobalt ferrite, for example, take cobalt chloride and iron chloride, and if we can expose this to microwave by reducing it with ammonia, then you can see the difference between conventional heating and microwave heating. So, if you are going to employ conventional heating, you can see that it is poorly mapping, whereas in the case of microwave heated reactions, it is faster, and then you get the single phase without any problem. So, you can make spinal compounds using simple reduction technique, and then you can isolate the final product with much ease. You should also realize making such spinal phase materials in solid state actually requires temperature more than 800 degrees C, where you can speed it up in no time. So, microwave can be used for such reactions, and also microwave for thermal hydrothermal synthesis, microwave can be used as a heating source than a furnace for making silicon crystals. And as you would see here, exposure to microwave, you can crystallize this particles in a much more clearer way. Another good application which actually can prove very cost effective is functionalizing carbon nanotubes. And carbon nanotubes, as you see here, this is the G band and D band of the carbon nanotubes, and as received and microwave exposed. So, the microwave exposed are showing a very clearer D band, which is due to the influence of microwave, and also compared to the as prepared carbon nanotubes, those which are exposed to different exposure levels of microwave clearly show that the carbon nanotubes can be functionalize with ease. Otherwise the conventional heating technique usually involves boiling it with nitric acid for a very long time, but digestion in microwave appears to be a very economic and a very facile route to functionalize the carbon nanotubes. Therefore, this can be extended for functionalizing carbon and nanotubes. Apart from synthesis, we can also use microwave for sintering purpose. As you know, sintering is a very long phenomena and it takes days, sometimes several hours for sintering any compound. When I mean sintering, we are making powder compacts and that can be sintered or that can be densified to theoretical density. So, that is densification up to theoretical and that is the use of sintering powder compacts. So, I will show the facile nature of microwave process, how we can achieve all this in a faster rate. This is one of our group's work way back. This is published in Physical Review B, where we have tried to synthesize a variety of silver selenide compounds using microwave. Silver and selenium, they couple with microwave very easily, but this compound cannot be made in open vessel. Therefore, this is a sealed tube experiment that you can try to do, and with different concentration of silver we can try to look at the magnetoresistance ratios. As you would see here, all the compounds with silver variation can be achieved, and a systematic change in the resistance versus temperature is also noted with a very clear dependency on silver composition. There is a systematic variation, as you would see. The insulator to metal transition is noted in silver selenide compounds, and one important point is when we take silver and selenium and mix it and make this sort of cylindrical compacts and then put this in a sealed tube and we try to expose it, there will be very bright flashes coming in this vessel, which will not only yield silver selenide formation, but it will also densify the compact. Densify the compact to such an extent, this is the SEM image of the silver selenide, that you would see there is no porosity, absolutely more than 99% theoretical density can be achieved simultaneously. So, this is one of a classic example of using microwave sintering. Not only you can prepare, but simultaneously sinter the compound to the final product. So, this is an example, and as you would see, if you take a EPMA, electron probe microanalysis of this, to map only selenium distribution, just to see whether selenium has segregated or it is uniformly distributed. All these minute spots that you would see here, this is due to selenium mapping, which means selenium is equally distributed in this short period. So, silver selenide formation is a very classic example of doing both the synthesis and sintering together at the same time, which is a very versatile route to synthesize products. And in sintering one of ceramics, for example, one of the important problem that we encounter is taking out the binder out of the matrix and then densifying it. As you would see here, conventional synthesis, the binder usually it is PVA, that is used polyvinyl alcohol, say 2% of polyvinyl alcohol is actually taken to a ceramic pellet like this, and it is actually heated, so to densify. So, this PVA has to be first removed before it goes through a size reduction, and as you would see, microwave assisted synthesis actually takes out the polymer binder in a much more facile way compared to conventional route. And also the linear shrinkage mapping, that is the densification, can be easily achieved using microwave reaction compared to conventional process. and this is another example of Titania nanoparticles which are sintered using microwave approach compared to normal sintering. As you could see here, these mono-sized grains are intact and they are more uniform, and better densification is achieved compared to normal sintering. So, microwave sintering is comparably much more effective, and also if you look at sintering of alloys of multi-component alloys, the sintering using microwave is much more uniform and with smaller grains compared to conventional stuff, because grain boundary and grain size can largely affect the properties of the final product. Therefore, you seem to get a controlled grain size growth in microwave, which can be exploited for device purposes. And there is another example of how microwave and conventionally sintered alloys can work out. As you would see, in the microwave case, there is not much phase separation, only one particular phase is promoted during sintering, whereas in the conventional case you see various phases are emerging out. This is because of inhomogeneous heating, or there is no volumetric heating. Therefore, these phase separations occur as you are taking the temperature from low temperature to very high temperatures. So, a conclusion on microwave sintering is it can be successfully used for a range of materials including metal powders. Advantage of the technique include significantly faster heating rates, lower sintering temperatures, and enhanced classification and controlled grain growth. Therefore, microwave one of the main application in inorganic materials is to do with sintering. We can also initiate high temperature reactions without a furnace, and I have discussed this in other modules also, but let me quote one example before I make some conclusion. Case of forming high temperature cubic phase of zirconia, we can try to achieve using microwave. How do we do that? We take zirconyl nitrate and we can use urea or carbohydrazide or any of the fuels, and this would actually give us zirconia nanoparticles, and this zirconia nanoparticles can either be cubic or tetragonal or monoclinic, either of this. As you would see from this microwave initiated reactions, you always get the high temperature phase. So, therefore, microwave can be used to completely avoid a furnace heating, and as you would see here very clearly that cubic zirconia phase is formed, and you can even dope cobalt in this case up to 30-40% with convenience without any impurity phase, and this is the typical magnetic curve for ZrO2, which shows a diamagnetic signal, whereas a 10% cobalt doped one shows a very clear hysteresis. So, you can achieve high temperature phases in no time using combustion, and these are other view graphs which tells us that such magnetic phases can be very conveniently prepared, and all this can be done in less than 5 minutes time because it undergoes a high temperature combustion reaction. So, to conclude, let me bring out few things. Typically, microwave energy decreases the kinetic energy barrier for reaction by altering bond vibrational energies of specific reactants. It also provides an expanded reaction range with lower temperatures and reaction times, which can obviously avoid side reactions, and this can lead to lot of cost savings. So, this is one of the main advantage, and compared with conventional methods, microwave synthesis has advantage of very short reaction time, production of small particles with narrow size distribution and high purity. For those of the hearers, I am just confining or limiting the use of microwave only to inorganic materials, but it is a big ocean, because more than 10,000 papers are recorded on microwave synthesis alone, where variety of organic synthesis has been achieved, and in organic synthesis usually it is the selectivity and the yield which is very important, and this has been enhanced using microwave synthesis. So, for those who are interested in organic synthesis, you can go to many of the websites and the published papers which will give you a classic outlook about how microwaves can be used for organic reactions also.